The essence of a bridge is not just that it spans over something, but that there's clear space underneath for a river, railway, or road. While this may seem obvious, bridges present a unique structural challenge. Unlike regular roads where forces are transferred directly into the ground, the forces on a bridge span get concentrated into the piers or abutments on either side. These substructures are among the strongest engineered systems on the planet, yet they are often built in some of the least ideal places for heavy loading, such as rivers and oceans with soft, mucky soils. Today we reveal the engineering secrets that prevent bridges from sinking. When you overload soil with a weight it can't handle, it's called a bearing failure. The foundation just sinks into the ground, similar to stepping in the mud. But what if you keep loading it and causing it to sink deeper and deeper? Congratulations. You've just invented one of the most widely used structural members on Earth, the humble foundation pile. How do they work, and how can you install them underwater? Let's dive into the world of deep foundations. A pile is a long pole driven or drilled into the ground. Timber piles, used since ancient times, are resilient and easy to install, but have limitations in length and strength. Concrete piles, available in various sizes and shapes, are more durable but require significant force to drive them into the ground. Steel piles, such as pipe piles and H-piles, solve this problem as they can be more slender and easier to drive deep into the ground. The main goal of a foundation is to remain stable under load. Piles achieve this through two primary mechanisms: end bearing and skin friction. The pile's toe can be driven into a layer of strong soil or rock, or the pile can rely on friction along its sides, compacting and densifying the surrounding soil as it goes deeper. Installing piles involves significant forces. A hammer drops a weight from a height, converting potential energy into kinetic energy, driving the pile into the ground. As the pile goes deeper, it compacts the soil, increasing resistance. This is evident in the blow count, where more blows are needed to drive the pile deeper as resistance builds up. Piles also resist horizontal loads from wind, flowing water, and ice or boats contacting the piers. To handle these lateral loads, engineers often use battered piles, which are inclined to take advantage of shaft resistance. While effective, driven piles can be noisy and disruptive, especially in urban areas. Vibrations from pile driving can affect surrounding infrastructure. Moreover, driving piles through hard geological layers or cobbles can be challenging. This is where drilled shafts come into play, solving many of these issues. A drilled shaft involves drilling a hole, placing reinforcing steel, and filling it with concrete. Underwater installations use a casing to keep the hole open, and a tremie pipe to pour concrete underwater, preventing dilution. Drilled shafts can also have enlarged bases for increased stability. There are many variations of deep foundations, each designed to address specific challenges. Continuous flight auger piles combine drilling and concreting in one step. Stone columns use compacted aggregate instead of concrete for compressive loads. Helical piles twist into the ground, reducing vibrations. Micropiles are used in restricted access areas, and sheet piles create barriers rather than foundations. The stability of piles depends on two primary mechanisms: end bearing and skin friction. End bearing piles transfer loads to a strong soil or rock layer, while friction piles rely on the interaction between the pile surface and the surrounding soil. As piles are driven deeper, the friction increases, providing greater resistance to movement. Engineers often use a combination of both mechanisms to ensure the stability of bridge foundations. Engineers conduct extensive testing to determine the bearing capacity and frictional resistance of piles. This involves load testing, where a pile is subjected to increasing loads until it reaches its maximum capacity. These tests help ensure that the foundations can support the intended loads and remain stable over time. Successful bridge foundations are a testament to advanced engineering. The Akashi Kaikyo Bridge in Japan, the longest suspension bridge in the world, uses deep foundation piles driven into the seabed to support its massive structure. Similarly, the Öresund Bridge, connecting Denmark and Sweden, relies on a combination of driven piles and drilled shafts to withstand the harsh marine environment. These projects showcase the ingenuity and precision required to build stable bridge foundations in challenging conditions. Engineers must consider factors like soil composition, water depth, and environmental impact to design foundations that will stand the test of time. Modern technology has revolutionized bridge construction. Drones and three-dimensional modeling allow engineers to survey sites with unprecedented accuracy, while advanced materials like high-strength concrete and composite materials enhance the durability of foundations. These innovations are pushing the boundaries of what is possible in bridge engineering. Modular construction techniques, where bridge components are prefabricated and assembled on site, reduce construction time and minimize disruptions. Rapid construction methods, like the use of self-propelled modular transporters, allow for the quick installation of bridge sections, further enhancing efficiency and safety. Building bridges in environmentally sensitive areas requires careful planning and consideration. Engineers must design foundations that minimize impact on local ecosystems and wildlife. This involves conducting environmental impact assessments, using environmentally friendly materials, and implementing construction practices that protect natural habitats. Sustainable bridge construction is an evolving field, with new techniques and materials being developed to reduce the environmental footprint of bridge projects. By integrating sustainability into the design and construction process, engineers can create bridges that are not only strong and durable but also harmonious with their surroundings. The future of bridge foundation engineering is bright, with emerging technologies promising to further enhance the stability and sustainability of bridges. Smart infrastructure technologies such as sensors and monitoring systems provide real-time data on the condition of bridge foundations, allowing for proactive maintenance and early detection of potential issues. These technologies enable engineers to monitor the performance of bridge foundations continuously, ensuring that they remain safe and stable over their lifespan. Innovations in materials science, such as self-healing concrete and corrosion-resistant alloys, are also being explored to extend the longevity of bridge foundations. While bridge foundations are less visible than their superstructures, they are critical to the stability and longevity of the bridge. Engineers use advanced techniques and materials to ensure these foundations can withstand immense forces and environmental challenges. Next time you cross a bridge, remember the incredible engineering beneath your feet that keeps it standing strong. Thank you for joining us on this journey into the hidden world of bridge foundations. If you enjoyed this video, please like, subscribe, and let us know your thoughts in the comments. Stay tuned for more fascinating insights into the engineering marvels that shape our world.